Well, I'd like to welcome you all to the annual forum that CEPA puts on. And this year we picked hopefully a topic that is of interest to a number of people. I'd like to frame my remarks in a way that will help frame how we ended up choosing the presentations for this evening. The topic, healthy bay, healthy fisheries, question mark. The question mark, I think, arises from the idea that we're spending a lot of money and effort on cleaning up the bay, as you all know from our last forum on TMDLs, which there was quite a bit of controversy over whether or not who should contribute most to what portion of the total maximum daily load. That argument is still in full force, as you can guess. But the question is, have we really begun to thought about what life is going to be like if TMDLs, quote, work? What will the future of the bay, what will it look like? What do you have in your mind, all right, that you think the bay will look like in perhaps 20, 40 years from now? I think that a lot of people think of bay restoration, they kind of think of 1950 clear water full of crabs and full of fish and all sorts of things like that. And the question is, will that be the future of the bay? Are we making the right kinds of decisions today that we think, or how are they going in the right direction? Are we prepared for the outcomes of the decisions that we're making today? And we thought we wanted to make that topic a bit more concrete. We didn't want that to be just a discussion about all the problems that are essentially in the bay. We wanted to pick a concrete example, and we wanted to talk about fisheries. So what I really want to do in my opening remarks is essentially frame our thought process, how we got to this topic, and perhaps get you thinking about what you will hear this evening. Well, it started out with this simple, naive question, all right, what is the state of the fisheries in the bay? And immediately we recognized that we weren't really interested in an accounting of the present ups and downs of fish catches, declining stocks, or attempts to restore the habitat. What we really wanted to know is, will there be sustainable fisheries in the future? Will they be the same that we know now, like crabs, oysters, or striped bass? Or will there be new species that we really have to worry about? What about aquaculture? Will we be able to manage the introduction of these new species, or will invasive species dominate? I think recently in the news, there was a limit on the menhaden catch. I think what was significant about the limit on the menhaden catch was not the fact that it was a limit, because that seems to be the standard reaction, all right, in terms of managing the fisheries. Limit the catch and hopefully it'll recover. What really struck us was the vociferousness of other stakeholders who really came to the fore, all right, in standing up for menhaden, in particularly the sport fishermen and the environmentalists who recognized that menhaden essentially represent a keystone species in the bay. Well, what's a keystone species? I think most of us remember from our either high school or early college courses that keystone species are those species in a food web that if they disappeared, the whole food web kind of tends to collapse. Really, they play a critical balancing role, all right, in ecosystems. They prevent the lower order organisms in the food web from overwhelming the ecosystem, and so forth on up the line. And so the need to have top predators in the ecosystem are important. But that was really the dominant question that emerged to us. How does one manage the ecosystem of a fishery? And we've sort of devolved this question, I think, to Professor Tom Miller, and he kind of as graciously has accepted the challenge to explain what I think is a very complex subject to us interested laymen. So I think when you listen to his presentation tonight, some of the questions that really came to our mind are, what is the state of science, all right, to predict ecosystem behavior? Oh, what is an ecosystem? What are boundaries in ecosystems? What constitutes an ecosystem? Ecosystems seem to have thresholds. Are there tipping points in these systems where changes may or may not be reversible or irreversible? What about managing and coordinating with related fisheries? How will managing a given fishery impact another fishery? What are the impacts on that? And perhaps most importantly, ecosystems are really dynamic systems. How will ecosystems change with time, and what will be the impact on fishery production? Well, the last question really led us quite naturally to ask about the effects of climate change. By 2050, the Bay will have a climate comparable to North Carolina. Well, to address this question, we have devolved this topic to Ray Nager to give us some insight. I think he is the lead author on a very comprehensive review paper on the impact of climate change on the Bay. And I think it's a very readable paper from a layman's point of view to be able, there's a lot of technical detail in there, but there's enough in there to really pique your attention if you would really like to look at it. So the sub rosa question, all right, is from all of this discussion, is what will the Bay look like in 20 or 40 years? All right, the TMDL process is not going to impact the Bay for another 2 decades itself. All right, but climate change is occurring in this same time frame at critical rates. And we're making these critical decisions now that impact the future. And again, I remind you, what are these decisions that we're doing now? I think the TMDL process is necessary, but the question we want to ask ourselves is it sufficient? I don't expect, all right, that we will answer these questions this evening. I do hope, though, that it will lead you to think more coherently and very deeply about what are possible solutions to possible outcomes, all right, that might be expected. So I do hope that our presentations this evening will shed some light, all right, into this very critical area. At this point, I'd like to turn the podium over to Tom Miller. Professor Miller is a professor in fisheries at the Chesapeake Biological Laboratory in Solomon's Island. Tom's background is really very apropos to the topic this evening. He has worked on ecology and reproductive dynamics of Atlantic cod off Nova Scotia. His work has varied from studies of fish early life history in the Northwest Atlantic and to Lake Michigan, to the role of small-scale turbulence in regulating feeding planktonic organisms, to the role of adult movement in regulating the population dynamics of skates. I think that he also has served as a member of the National Research Council's panel on water use in the San Francisco Bay area and Delta. And are you a member of the STAC? You're not a member of the STAC. Okay. At this point, I'd like to turn it over to Professor Miller.
First of all, thank you all for coming this evening. I must say I'm kind of surprised that Al actually continued to extend the invitation that he made to me at the first time that we met. was in a restaurant in Solomon's, and Alan and several other gentlemen were out on the back deck of the Kingfisher restaurant. And I was running a little bit late, and I was in a rush to get to them, and I didn't realize that the sliding glass doors to get out on the deck were in fact closed, and moved straight into the sliding glass door. I think they didn't see, because if they hadn't done, they certainly wouldn't have invited me to continue. So as a fisheries biologist, it's really easy to be depressed. These are the sort of headlines that we're faced with. Largely stories of decline. And I suppose I have to remain somewhat optimistic and view the glass half empty, rather view the glass half full rather than half empty. So what I want to do tonight is to try and answer some of the questions that Al laid out at the beginning. And I'll preface it by saying that I do think that there is a bright future for fisheries in the Chesapeake that are both sustainable from an economic and sociological viewpoint and sustainable from an ecological viewpoint as well. So I'm going to start with a picture of St. Paul's Cathedral in London, not because I think we need divine intervention to get there, but because I want to tell you a story, an analogy. What I want to focus on is this bridge in the front. This is the Millennial Bridge in London. It was built to celebrate the millennium. The first bridge built over the River Thames for 150 odd years. It's a pedestrian footbridge. And Sir Anthony Carrow, who was the architect of this, knew when he designed this bridge the number of pedestrians that he thought would be crossing it. He was given a very clear design goal. He knew the tensile strength of the steel that the bridge is built out of. He knew a lot of the physical properties of the steel. He could build a computer model of the bridge, of all of the joints and all of the welds and all of the flow of the water to ask whether it was sustainable. He could build a physical model of the bridge and ask those same questions. And yet when this bridge opened, Londoners rechristened it within the first week the Wobbly Bridge. Because in fact when people walked over it, it wobbled. They hadn't really taken account of the harmonic characteristic of the people on the bridge. And so there was a massive redesign of this bridge involving many millions of pounds and substantial court cases as to who was responsible. Was it the architect? Was it the designer? But in the end, they resolved the problem. The bridge no longer wobbles. The name, of course, stays. But the advantage here is, again, the designer knew all the physical properties. In fact, knew that the physical properties were the same when he designed it as when the bridge was built, as they will be 50 years from now. And he could build a series of models to really represent that system. So I'm going to compare that, draw that as an analogy to this, which is the food web of the Chesapeake Bay. Each of the circles represents either a species or a trophic guild of species. The lines represent energy flow between them, and the size of the lines represent how much energy. And in orange is everything going into Menhaden, and in green is everything leaving Menhaden. So you can look at this and see that adult Menhaden eat a lot of phytoplankton, and they're eaten largely by striped bass, although there's some going into sandbar shark, and there's some should be going into weakfish. So what's different about this system than the Wobbly Bridge in London? Well, the first thing is, those of us who are asked to advise the managers, to provide the scientific architecture, if you like, to manage this system, don't know all of the ecological measures, the tensile strength equivalences of this network. And perhaps what's more important than that, we don't know that it will be the same 20 years from now that it is today. because it is certainly different today than it was 20 years ago. There's a lot more chance events going on in here, a lot more of what we call stochasticity driving this ecosystem. And perhaps as important as those two things, unlike the wobbly bridge, we're not given clear design goals. There's not a clear statement of what society wants from this ecosystem. And so I'm going to continue that analogy looking at those 3 points of not knowing the ecological characteristics, looking at the role of chance events, and looking at the role of lack of design characteristics as to move forward how we manage fisheries and how we might manage fisheries into the future. So let's start with what's the sort of data we have to manage fisheries. These are the latest results from the Blue Crab Winter Dredge Survey. This is the standard survey that we use each year to analyze the abundance of crabs in the Chesapeake Bay. It's been conducted since 1990, all the way up to this year, 2013. And we measure them in the winter when the crabs are buried in the sediments. They're not moving around, so it's much more like counting tree trunks than it is like counting moving fish. So we can get a very accurate and precise measure of abundance. And what sort of things you see? Well, you see very large variability from year to year in young crabs, age 0. In fact, last year there was record abundance of young crabs. This year there's almost record low abundance of young crabs. That sort of variability is to be expected. You'll see that there's also variability in some of the older stages, but not quite as much. That variability is slightly less. But these are the kinds of data that we have to try and start managing a fishery. So how do we start managing a fishery? Well, I'm going to show you this cartoon over a series of slides, and I'm going to build up from this simple fishery of a somewhat unusual trawler, which isn't quite appropriate for the Chesapeake Bay, catching somewhat unusual fish. And we think of this as a fisheries scientist advising the management agencies as this relationship. The number or biomass of these fish next year is equal to the growth, how much weight they put on, plus their recruitment, which is how many young fish are born each year, minus the number that we catch in the fishery, minus the number that die from all other causes that we call natural mortality. That's the most complicated equation you're going to see tonight. So just think of what the pattern is. So thinking back to that analogy with the bridge, and the fact that the bridge, the physics are deterministic, they're the same last year as they are this year and the same as they are next year, what's different about this system? And as I showed you with blue crab, what's really different about this system is this recruitment, the number of new individuals we get each year. We can make guesses about M, growth tends to be relatively constant, and we can do a pretty good measure of how many crabs we catch. We do a horrible job of trying to forecast what the numbers of recruits will be. And why is that? Because this is the relationship between the number of female crabs and the number of offspring that they have. Now, if I was to give that to an engineer and say, tell me how thick the steel beam has to be to carry a weight, a certain load, and this is the relationship, they would throw their hands in the air quite understandably and say, I can't do it. Or worse, they would say, I'm going to just assume a straight horizontal line through that. Right? And think of what that means. A straight horizontal line means that if the average is, let's say, 30 million recruits, it's going to say there can be 30 million recruits when there are no spawning females. And biology doesn't have very many laws, but one law it does have that's inviolable is if there are no mummies, there can be no babies. So we know there has to be some pattern in there, but what that pattern is somewhat opaque. And how the environment affects that pattern and how the changes in the environment might affect that pattern are also opaque. An example will be, this is menhaden. This is recruitments of menhaden into the Chesapeake Bay since 1960, from 1960 to 2010. Huge variability. It's not uncommon for fish like menhaden that serve as prey, as forage for other fish, to show 10 to 100-fold variation from year to year. And yet we're expected to provide scientific advice on how to manage that system in the face of that variability. It is a remarkably challenging path. How do we try and understand that? Just to give you an idea of how sophisticated it can become, I'm just going to run this. I don't think I can do it from here, but let me just run it and see it. You're going to see these black particles move around. They are particles that represent menhaden larvae being spawned offshore, and they're being moved around by the ocean currents, and they're going to start recruiting to these estuaries. At the moment, none of them have reached the estuaries. As they age, they die, and they become fewer and fewer, so the contrast in these particles becomes whiter and whiter until they'll disappear. And so, at the end of this simulation, we have a distribution of particles up and down the coast, and we say 4,000 or so of them go into the Chesapeake Bay. If we change the distribution of spawners, we fundamentally change the distribution of these numbers on the outside. Where they spawn makes a huge impact on whether they arrive in the Chesapeake Bay to be part of that recruitment. This is fundamental uncertainty that we will probably never fully resolve, even though these models are really sophisticated and we get a great deal of satisfaction of putting them together, and we can begin to ask, why does the Chesapeake Bay get sort of a third of the recruits? Why does Ocracoke get very few? Why does Long Island Sound get very few? But they don't really help us very much in the management question, to be perfectly frank. But this is the sort of things we're trying to struggle with to try and understand those sources of variability. So we're going to turn back to this cartoon and ask, given all that uncertainty, how should we manage this system for sustainability? And the only way we can manage it, the only thing that we control, is this fishing, that F term. And what we do is we assume that fish create far more offspring than they need, and that any excess over what they need we call surplus production, and that we can harvest. That surplus production might be required to support the predators of this species. It might have a significant impact on the ecosystem, serving as prey or predators on other systems, but we assume we can take it all as surplus production. And further, we assume there are only really two stakeholders in this decision. Deciding what F should be is a balance between the commercial fishery interests and the managers, presumably protecting societal views, but not necessarily. And remember, it's the commercial fishery interest, not the consumer's interest. It's maximizing profit for the commercial fisherman. It's not necessarily minimizing costs to the consumer, which might be another legitimate goal. And to achieve that, we conduct complex mathematical and statistical exercises called stock assessments. Now, I'm not going to show you a stock assessment because that would put me to sleep as well as you, but I'm going to show you the output of how we try and advise managers as the results of that stock assessment. And so we give them what's called a control rule. And on the bottom is abundance. So you go from very few to a great many. And on the side axis is the exploitation rate from very low to very high. And you can think of this as your own personal finances if you want. This is the amount of money you have in the bank from very little to being very rich. And this is your spending rate from being miserly to being a big spender. And the first thing we do is we say, there is some minimum amount of fish or crabs or money in your bank that you need to meet your future obligations. The future obligations here are sustaining the next generation. In fisheries, if you have less than that, you're said to be overfished. In a bank, in a financial, it might be overspent, but overfished is the word we use. Equally, no matter how abundant they are, or how much money you have, if you catch them too fast, or you spend it too fast, you will become overfished very quickly. So to avoid that, we set up a maximum fishing rate level, which we call overfishing. So a species could be overfished, it could be experiencing overfishing, it could be both overfished and experiencing overfishing at the same time. And what's left in this green area is what we call sustainable. We know, generally, that the relationship between abundance and exploitation follows that line. And it is our job as scientists to define these red boxes. It's the manager's job, or the stakeholders' jobs, to define where in this green box do you want to be. And I'll submit to you, and I'll try and explain why, we do a pretty good job, of defining these red boxes. We do a horrible job of deciding where we want to be in the green, because there aren't enough people involved in that decision. What does this look like in real life for blue crabs? This is it for blue crabs. We had a long period of time when we had low abundance and high exploitation rates, and then in 2008 the management agencies finally began to see sense and started conserving female blue crabs, and we saw a very dramatic increase in abundance, and we're down back with a lower abundance but a lower exploitation rate at the moment. So we are certainly sustainable with a blue crab fishery currently. So that's how you would manage the Chesapeake Bay if there was one fish and one fishery. But that's not the Chesapeake Bay, as I showed you at the beginning. It's an ecosystem. It's lots of species and lots of interests trying to catch them. So we can compare perhaps a commercial fishery and a recreational fishery. We do that by just adding two sources of fishing mortality. Mathematically, it's very simple. But as always, what might be mathematically very simple, when you try and do it, becomes very complicated, because now, even though the toolbox remains the same, the people making the decisions are different. And they have different legitimate goals for where they want to be in that green box. And they may not all want to be in the same place. And the decision of where they want to be is not a scientific one. I can't get up here as a scientist and say, you should be in this spot. It has to be a political, a sociological, an economic balance among these stakeholders to say, where do you want to be in the sustainability area? So this is how we do it typically. We do the assessment, we give it to the managers ask the public, and then they make a decision, and they either accept the advice or they reject it. And if you talk to most people involved in fisheries management today, as a stakeholder's point of view, they view this as being characterized by three words: invite, inform, ignore. We invite them in, we tell them what went on, often in highly sophisticated, highly technical, highly mathematical language, which they have no hope of understanding. And then when they tell us what they want, we say, well, I'm sorry, we're going to do the other. And people understandably get remarkably frustrated. So is there a better way? And I'll submit to you there is a better way. It's to put stakeholders in the middle of this and make us scientists subservient to the stakeholders. Make the stakeholders ask us, challenge us to meet their questions and their demands. And you might think that that's a difficult task, and it is, but it does work. We've done this exercise with recreational and commercial fishermen in Florida. We started off trying to explain how a fish stock works like this. This is the exact slide that we used. I think everyone can understand that we have baby fish. They move, they grow and mature. Some of them reproduce and produce more baby fish, but some of them die because they're caught, and some of them die because natural deaths. In a 1-year period where we met them 4 times for 4 days each time we met them, they went from this to this. Highly sophisticated mathematical representations of everything that that cartoon showed them, and they understood everything that was in there. They couldn't do the mathematics. They don't need to be able to do the mathematics. They need to understand and believe that their concerns are represented in those equations. And that's all they need to believe. And when they do, they come up with really sophisticated ideas. And when we presented these to the managers, in fact, when the stakeholders presented these to the managers, that they didn't want to achieve status quo, they wanted these range of very specific options considered, that they should only have a 2-fish bag limit, the minimum size should be 28 inches, not 24 inches, or 32 inches, and they could predict what the effect on abundance, spawning stock biomass, would be, and they could predict what the effect on the exploitation rate could be. The managers were absolutely amazed. I literally saw managers sit there with their mouths open because they had never had informed stakeholders in front of them telling them what they wanted. And this is where I believe we should be going. So, if we can do that for one species, can we do it for multiple species? Here's an example of the Chesapeake now. We've got both fisheries. We've now got 2 species. We've got striped bass and our unusual fish. And we represent that as 2 fishing fleets and 2 different sources of mortality. We're now specifically estimating the mortality from that species. And we can do all of the mathematics. So here's an example where we look at the sustainability of striped bass when we start fishing everything else at sustainable levels as well, recognizing that it is a connected network. It's not a series of independent stovepiped species that don't interact with one another. So if we fish striped bass, just striped bass, our work says that you can reduce it to about, or it can be reduced to about 67% of its, if you fish just striped bass, you can take about 61% of the maximum yield safely. If you just think you're fishing striped bass and ignore everything else. If you now say that, well, I'm actually fishing striped bass and menhaden, you can only take about 50% of the maximum yield of striped bass. If you say I'm fishing striped bass and 5 other species, you can only take 27% of the striped bass. And if you say I'm going to fish all 9 species sustainably, you can only take 25% of the maximum yield of striped bass. So the mathematics is there, the science is there to help inform. What's not there is the question, do we need to take 9 species at their maximum sustainable yield? Do we want to take 9 species? And if so, in what proportion? We might choose one where we keep all of the menhaden in the Chesapeake Bay because we value striped bass more. Or we take all of the menhaden because we don't value striped bass as much. And notice, value is not a scientific word. Right? It's a policy word. And that's why the stakeholders have to be engaged. lots and lots of stakeholders when you get to multi-species management, not only all of the different fisheries and the managers protecting society, but there are ones protecting or representing the predators. And they may be other fishermen, they may be NGOs, they may be farmers, they may be a whole range of new stakeholders that aren't used to being involved in fishery questions. We can really begin to expand this, and we are. We can begin to involve habitat. And habitat affects this recruitment, because habitat usually affects young fish when they're growing. And we can certainly do that, and we can run all kinds of models, and I'll just skip that one, because I know I'm talking longer than I should. We can ask the question, what happens if you preserve or don't preserve habitat? So this is an example in Delaware Bay that PSE&G asked us to look at. And PSE&G were required by the Nuclear Regulatory Commission to get a license for its nuclear power plant to start restoring marshes all up and down the Delaware Bay to offset the fish that are taken in their cooling waters. They said to protect the species that are caught in the cooling waters, build marshes, because that's where these fish like to live. And PSE&G said, how on earth do you know that how much marsh we have to build to protect how many get sucked in to our nuclear plants? And so we said, well, this is how much. If we hadn't built the marshes, if we hadn't built the marshes by 9%, we would have lost about 4 metric tons of biomass. So we are at the point where we can provide very specific scientific information that allows stakeholders to make those trade-offs that are, again, aren't scientific questions, are societal questions. So what about then the maximum that we can take this to, this ecosystem-based management? And that's the buzzword that you'll hear a lot of now. We need to move towards ecosystem-based management. What does it include? Well, it's going to include perhaps regulating development, because development affects runoff patterns into the bay, which might affect water quality. It might include agriculture, because agriculture produces products through fertilizers or others that run off into the bay and affect the system. Industries. And we're not only going to start modeling the fish species, but we're all going to start modeling the tiny microscopic animals on which they feed, the worms that live in the sediments, the oyster reefs. And this gets complicated. And so how do you provide stakeholders the guidance to know whether their options work or not? So I'm going to suggest to you that the way that we're going to do that is by setting objectives that are long-term and strategic ones, and then defining operational indicators that we want to look at. And remember, an indicator reflects how far you are from your goal. And we use them all the time. We use leading economic indicators. We don't measure all the money going through the economy. You'll hear on the news, the leading economic indicators are up, they're down. We don't know what they are, but we know they're up or down, and we know that we don't want them to be up or down. That's the kind of decisions that I think we're going to come to. But what's the problems with indicators? Indicators can give you good or bad information. So if you think about this as an indicator in the black line through time, and we decide through some process that we want to be at that dotted line, we could have a period where you're below the indicator is below the target, and that gives you good information. And there's a period where you're above the target B, and you might do something else. So you can change what you do management-wise based upon this indicator. But in reality, indicators don't look like this, they look like this. I showed you that with the blue crab. Lots and lots of variability. And so what happens? Well, sometimes the signal, that is your indicator, says you're below the target. and it was really true, and you should take the action. You get a hit. Sometimes the indicator says you're below the target, but the event really didn't happen. You really weren't below the target. It was variability that told you what was going on, and you get a false alarm. Other times the indicator says that you weren't below the target and you really weren't, and you get good information that way, and sometimes you get true negatives. This kind of idea of understanding what the information is telling you and how you have to respond is the challenge that we face going forward. So we're going to, I didn't remember I'd animated this. I spend all this time animating a line and then completely forget. I apologize. So what's the challenge then? The challenge is what comes first, the goal or the stakeholders. Why is that a challenge? Because there is no absolute goal that's true for everyone. And who you invite in the room is going to change the goal that you set. If you set just commercial fishing interests, you're going to get one answer. If you put commercial fishing interests, recreational fishing interests, NGOs, EPA, whoever you want in the room, you're going to get a different answer. So deciding how you do this becomes important. The second question is, given that you have decided a goal, and a goal might be Chesapeake Bay health, the most difficult question is, how do you cut up the pie? That's always the most challenging question we face. It's not how big the pie is. Science does a pretty good job of telling you how big the pie is. Science can't tell you how you cut the pie up. And that's where the rubber will hit the road with ecosystem-based management. And then, given that someone's decided how you cut the pie up, how do we use that indicator to tell managers how they should change their behavior is also somewhat troublesome, but I think we can do that. This is the part that I think will become the very, very difficult decisions that we face. How might we do that? I'm going to suggest that for the Chesapeake Bay, a good place to start is to set an absolute cap on all harvest. Not just menhaden, not just striped bass, but say the total weight of fish and shellfish you can harvest from this ecosystem is, for example, 300,000 tons. And you now have the job, that's how big the pie is, you now have the job of saying, how do you want that 300,000 tons sliced? Not a science question, that's a socio-political question. What it does is that it promotes explicit recognition of the trade-offs. If a striped bass fisherman, whether commercial or recreational, sits in that room and says, I want a bigger slice of the pie, that person has to explicitly recognize that their bigger slice of the pie comes at the cost of someone else's pie piece. And that is a big change in fisheries management. We're not used to that. We're used to arguing how big the pie is, because if I get a bigger piece of pie, that's great. It doesn't affect the other person's pie. Putting a complete cap on the total systems removals would make us think about trade-offs. We could also do total catch of, say, predatory fish, or ratios of fish in the upper water column and fish in the lower water column, or menhaden and striped bass. There are lots of candidates that we could do, but all of these promote the recognition of trade-offs in an ecosystem. How do we move forward? Lots and lots of people are thinking about how to do this. This is my pitch for science. We can't do those questions. We can't tell you how big the pie is without improved science. Student training, staff development, data infrastructure. Same message we've been giving for a long time, but I think there are compelling reasons why we do that. Just remind you, this is the real question. Goals and stakeholders, how's allocation determined? That's where we've got to go. But most of important and all, we need to move towards setting goals. So I'll stop there And Al, I don't know if you want to postpone questions to the end or what?
Defer questions to the end.
Okay.
Oh, thank you, John. Are you set? I think what you've just heard is kind of a fascinating idea that we have to consider the ecosystem from a total point of view rather than individual species point of view. In one sense, though, is that better? Okay, thank you. Dr. Tom Miller has really been talking about the present, and he's sort of espoused more or less, I would say, a static viewpoint. But what we're really talking about is a dynamic situation in which the ecosystem now is beginning to change underneath the idea of managing the species. So the dynamic conditions that we're about to be introduced into this equation, namely climate change, are going to have a critical impact on fish production. To comment on this particular area, the idea of what the future impacts on fish production might be, we've asked Dr. Raymond Nager, who's professor of oceanography in the Department of Meteorology at Penn State. His research covers two areas in marine biogeochemistry and the impact of climate change in estuaries like the Chesapeake Bay. His current research is focused on nitrogen and carbon cycles of the coastal waters in the eastern United States and the long-term salinity changes in the Chesapeake and Delaware Bays. But I think more importantly, he is the lead author on a very critical review paper on the impact of climate change on the Chesapeake Bay and fisheries in the Bay. And I think as lead author of that, he's critically capable of talking to us about what the future might entail of fisheries in the Chesapeake Bay. Thank you.
Well, thank you very much for coming out on a lovely evening, spending it inside here. And thanks for the opportunity for me to tell you about some of my research and some of my work with collaborators. And this particular effort, I should say, is very stimulating one and very challenging and sometimes daunting because to understand climate change impacts on an ecosystem really, an estuarine ecosystem really means pulling together a very diverse group of individuals and expertise. And the problem is, from one who's leading that effort, is that you don't really know everything as deeply as you would like. And fish is probably a perfect example of that. I'm not a fisheries biologist. I'm an oceanographer, and my focus really is on biogeochemistry and a little bit on ocean circulation and salinity change. But I was really fortunate to have some very interesting and knowledgeable collaborators, and I'll point those out here. That's Bob Wood, Dave Secor, and the CERC scientist, Denise Breitberg, who really did the heavy lifting on the fish part of this synthesis. And I cut out a piece of the paper and I made a handout of it, and I'm happy to, I have my contact information there. If you want the reprint, I'm happy to send it to you. So I'm going to be walking you through some aspects of climate change, but try to focus really on the parts that are related to fish. I'm not really giving a primer on climate change. I'm happy to answer any questions about the causes of climate change. But in short, I'm taking the consensus view that the warming that we've experienced and are very likely to experience in the future is largely human-induced, and it's a result of increased concentration of greenhouse gases mainly from fossil fuel emissions. So with that, let's just see what's happening with Chesapeake Bay now. This is not something, climate change is not something that, and global warming is not something hypothetical for the bay. It has been experiencing warming that's largely consistent with anthropogenic climate change. And here's some data that show there's lots of variability, but a pretty clear signal of warming throughout the estuary. And another way the estuary is changing is in terms of sea level, and there are significant increases in sea level. About half of this is related to climate change, and the remaining half is due to the natural subsidence that's occurring throughout the estuary. And this is already having impacts. We're losing some islands, there's increased erosion, and so forth. So climate change is something that's going on very actively in the estuary now. Yeah.
Excuse me, where's Sewell's Point?
Where is Sewell's Point? That's in Virginia.
Okay,
Yeah.
so further down the bay.
Right.
So it's from Baltimore down to the bay.
Right, right, yeah. Yeah, there are variations in sea level rise throughout the bay, but a reasonable figure for the bay as a whole is 3 or 4 millimeters per year. Okay, and you can see
So
it.
Baltimore being further up and Sewell's Point being closer to the ocean, there's obviously some tidal issues as well.
I'm not sure what you mean by that.
I'm just looking at how you're measuring this from your end rising.
Okay,
So I'm just trying to say Baltimore is much further up the bay,
right.
more on the river estuary, and
Yeah.
Sewell's Point is closer to the mouth
The
of
ocean, right, right. But the rates are not dramatically different between the two places. I guess it
Okay.
looks like it's a little bit higher, the slope is a little bit greater in Sewell's Point than in Baltimore.
Okay, thank you.
Yeah. Okay, so that's sort of what we have observed in the bay. And one of the great things about studying this estuary is that it's, compared to others, it's quite well monitored. And we have, as much as scientists would like more data, comparatively speaking, it's well monitored. So this is kind of what we can expect for the future for this particular region. And an important point to make is that different aspects of climate change are known with different levels of certainty. So increases in CO2 are virtually certain unless there's some sort of catastrophe that stops humans from emitting CO2 all of a sudden. With that will come higher sea level. That's really like a global phenomenon. Sea level is sort of an integrator of climate change globally. So that's virtually certain that sea level will continue to rise. Very likely is continued regional warming and precipitation patterns. The climate models suggest very consistently that winter and spring precipitation will increase. And then with somewhat less certainty, we can expect precipitation to become more intense. That is, it may not rain as much, but when it rains, it will rain harder and in shorter events. That will lead to stream flow being flashier, and stream flow will probably also go up in the winter and spring. And then finally, the intensity of storms is more likely than not to increase. So this is just a summary of the literature on projected climate change. Okay, so what does this mean for the estuary? This is a figure that was created in a report that I would commend to you. It's a Maryland climate change impact assessment that was led by Don Bosch. And this shows the estuary, the warming of the estuary through what its temperature would be in the future compared to what the temperature is along the coast now. So just to take the extreme point, and it looks at 2 different time periods and 2 different emission scenarios. So this is a relatively high emission scenario known as A2, and a relatively low CO2 emission scenario known as B1. And if you look out to 2100, the summer temperature of the bay under a high emission scenario would be comparable to what summer temperature is for Florida estuaries now. That's kind of an extreme case. And if you go to the low emission scenario, you see still warming, but not nearly as dramatic. So the summer temperature would be more comparable to a South Carolina estuary. Now this doesn't explore the full range of possible emission scenarios. It's just kind of a sensitivity analysis. And so the point I like to make with this slide, I guess there's 2 points, is that climate change really has the potential to very dramatically alter the estuary. And the second point is that particularly as you go out towards the end of the century, it really matters what the emissions pathway is. There's a cumulative effect of emissions. The climate system has a lot of inertia. So in the short term, the emissions pathway doesn't mean that much. That's why in 2050, these two are fairly close to each other, but they spread apart in the longer term. So let's move on to fish. How are fish going to be affected by climate change? Well, there's lots of ways that fish can be affected, and Tom laid out some of the ways that fish are impacted. One is through habitat, and we'll talk a little bit about that. Some of the more direct effects are from temperature. Fish care about what the water temperature is because they breathe. They care about how much dissolved oxygen is in the water. They care about habitat, such as submerged vegetation. Some fish care about how acidic the water is and other aspects of the water, its circulation and salinity, other aspects of the food web that Tom pointed out, how everything's kind of connected. This makes really the prediction problem for climate change really very daunting, and we can only make some very broad generalities. And then there's more subtle effects about predator-prey interactions and how the seasonal timings might be changed as climate changes. So I'm really just going to discuss a few of these. These top four I'll touch on, and then for discussion, all you can ask Tom about all those other things, because I really don't know. Okay, so let's talk about warming. The simplest sort of impact one might expect is that species will shift northward, okay? And this comes from Bob, Denise's, and Dave's synthesis. So what they suggest, these are really just suggestions about what could get pushed out. In other words, what's kind of at its southern limit now are all these fishes. And I've got the soft clam here, but other things, perch, striped bass, flounder, and so forth. Species that are to the south now that might move in are some shrimps, some flounder. I've got the Spanish mackerel here, kingfish, and other things. And so that's one possible scenario. One thing to keep in mind is that some low salinity critters, like this dark false mussel here, which lives sort of in the upper parts of estuaries, might have a hard time moving because they would have to get out into salty waters that they don't like. Okay, so that presents a challenge for some species. Okay, there could be some certainly good things about warming for fish. They'd have longer growing seasons, and I'm showing you here the striped bass would have a longer growing season. This is something we've already seen in the estuary, reduced shoreline freezing. That would actually open up some habitat, so that could be an advantage. And one thing is that is improved overwintering. So the blue crab stands out as a species that could benefit from the ability to overwinter. But overwintering can also cause pests and diseases to last longer, and this is something we've actually seen already with the oyster and the disease that the oyster experiences, because the parasite can live now, do better throughout the winter, and then become more virulent and harmful to the shellfish. And it's been demonstrated reasonably well that the north projection, the progression of oyster disease has essentially followed winter warming. And this is work from folks at the Haskin Shellfish Lab, like Susan Ford. So this is something, climate change, this is a way that climate change has already affected fish. Okay, let's move on to oxygen. As you know, fish need oxygen, and this shows the kind of minimum levels for various types of fish. A striped bass need a lot. Spawning habitats, spawning fish tend to need more oxygen as well. So we want to know how oxygen is going to change in the future. And of course, this has been a big concern for the Chesapeake Bay already, because oxygen levels have declined quite dramatically as a result, ultimately, of eutrophication, the stimulation of phytoplankton blooms from excess nitrogen coming into the estuary from the watershed, from fertilizer, from untreated sewage, that sort of thing. So these blooms, when they settle to the bottom and decay, they consume oxygen. And so what we've seen are long-term increases in the volume of hypoxic water. So this is about 60 years of the hypoxic volume, and it's gone up quite dramatically in the estuary, and it's largely attributed to the increased loading of nitrogen to the estuary, and particularly how much nitrogen comes in the spring, which it tends to feed the summer blooms and lead to the hypoxia that occurs mainly when the water is warmest and most stratified, and that's in the summertime. So we could think, how might climate change affect dissolved oxygen in the bay? And as we saw in the past, when the spring flow is higher, that tends to stimulate more photosynthesis and more decomposition, and tends to decrease bottom water oxygen. It also, by putting kind of a freshwater buoyant lens on the surface, tends to inhibit the vertical exchange of water, which naturally aerates the bottom, and that increase in stratification will also lead to decreases in bottom water oxygen. There's another effect, and this is more certain. The water is going to warm up, and we know very well the relationship between how much oxygen can dissolve in the water and its temperature, and that decreases as the water warms, so that'll also lead to decreases in bottom water oxygen. Temperature can also stimulate the food web and lead to more photosynthesis and decomposition. So it's kind of, there's many arrows pointing towards further decreases in dissolved oxygen. This is all qualitative, I should say. So we haven't actually modeled this, and I think that's an important research need. And then finally, CO2, increases in CO2 itself tends to increase the respiration parts of the food web, and that will also lead to decreases. So again, from a qualitative standpoint, there's many things that are pointing towards decreases in dissolved oxygen simply due to climate change. So what would be the effect of that? This is a calculation that Dave Secor and one of his collaborators did, showing habitat suitability for young of the year Atlantic sturgeon. And the sort of white areas here show the suitable habitat. And as you warm the water only by 1 degree Celsius, you pretty dramatically reduce the suitable habitat. Okay, not only do you have less oxygen in the water, but you also increase the oxygen demands of the fish as well. So both of these lead to substantial declines. Okay, so let's move on to the next aspect, the submerged vegetation. How might we expect submerged vegetation to change? It's a very important habitat for fish, as Tom has already pointed out. Tidal wetlands also fall into this category, and here's an example of a blue crab caught in an SAB bed. And of course, it's a good foraging grounds for fish as well. It's nursery grounds and foraging grounds. And this is another example of how at least climate variability has affected submerged vegetation. When we have very hot periods, eelgrass, which is an important submerged vegetation in the bay, when we have a hot summer, it tends to be cut back because eelgrass is already at its southern limit. So this is like, we'll get pushed, one would expect it will get pushed out of the bay with further warming. And so we have some evidence from variability, at least, that SAV declines when you have a hot summer. You can see the declines in the beds here from part of this is seasonal, going from June to December, but it also results from the very extreme heat that was experienced here. So pretty large declines in the grasses. So we'll draw another diagram here. If we expect spring stream flows to increase, that will bring more nitrogen to the bay, stimulate phytoplankton blooms, decrease the water clarity, and SAV as a plant needs light to reach the bottom. It will get less of it, and so one would expect the SAV to decrease as a result of that. Higher temperature also, at least for eelgrass, would tend to cause the SAV to decrease. And then also, SAV also do need some oxygen. If some of that comes up into the shallows, that could cause an SAV decrease. One positive place is that CO2 is actually food for plants and can stimulate some plants, including SAV. So this might counteract some of the declines we would see from other aspects of climate change. Okay, so the last thing I'll talk about in terms of how climate change might impact fish and shellfish is on acidification. And seawater is naturally alkaline, but it's becoming progressively less alkaline as CO2, which is combines with water to become carbonic acid, makes the water less alkaline. And so there's been some work done incubating oyster larvae under different levels of CO2, and as the levels increase, the rate at which those oyster larvae can build their shells declines. So this is a negative impact of increased carbon dioxide directly on a calcifying organism, in this case, the oyster. So the bottom line, I would say here, even though the information is incomplete, is that climate change is going to significantly impact the bay, and it presents additional challenges to restoration and fish management. So I think there's some aspect of climate change that's unavoidable because of the inertia of the climate system, and we have to be aware of that, and fisheries management and restoration efforts need to be cognizant of it and to consider it. And so that means adapting and managing what's unavoidable. However, we don't have to have that estuary move down to Florida, right? That's a big change, and probably I would say it's probably not one for the better. It's my personal opinion about that. And so how do you avoid that situation, which I think is very likely unmanageable? That means reducing emissions. So of course there's many reasons for us to reduce the amount of carbon dioxide going into the atmosphere. This is yet another one. It's going to affect our estuaries significantly, and not completely negatively, as I pointed out, some benefits, but I think largely negatively. So, I obviously have to put in what you can do about it. I may be preaching to the choir here, but I'll say it anyway. Anything that reduces nitrogen going into the water, carbon dioxide into the bay is a good thing. And you can actually save money doing those things, and some things are to, avoid your car if you can, bike and walk more, improves your health, things you can do with your diet, make it more vegetarian. You don't have to be completely vegetarian, but there's definitely a lot less energy that goes into producing vegetables, a lot of things you can do in your house. And above all, particularly for this group, which has a strong policy bent to it, it's get out and get informed and affect policy. I mean, we need a climate bill, really, is what we need for climate change. At least the Bay is moving in the right direction with the TMDL and trying to do something about that. We need like a TMDL for CO2 is what we need, really. And that's got to be done globally. It's a very difficult problem. It's no doubt very difficult, very challenging problem. But I like to point out is that we've had many environmental success stories, and we shouldn't forget those. And I put one up here now, and that is the acid rain nitrogen deposition story. It's really a spectacular success. It's dizzying how impressive this tremendous decline in the acidity and the nitrogen content, sulfur content of our rain as a result of the Clean Air Act. And it's saved a lot of money, okay? And so it's been a win-win situation. And this is a graph that shows how the cost really hasn't changed, the electricity generation has gone up, and the emissions have gone down. I'm not saying climate change is this easy, but I'm saying that we got a lot of pushback from trying to do this. And people told us it was too expensive, and it couldn't be done, we'd lose too many jobs, and so forth. And it just, you know, it didn't happen. We pushed, and we were successful, and I think, you know, we can be successful with climate change and with cleaning up the bay. So I'll end there. Thank you very much.
Thank you, Ray. At this point, we move to our discussion, and the discussion will be led by Dr. Janet Davis. She's Executive Director of the Chesapeake Bay Trust, and most of you actually know her, by the way, if you contribute to your license plate, all right, on your car. So if you don't have a license plate, go out and buy the Chesapeake Bay Trust license plate. That's a plug for you. So I think you actually know her. She's a marine ecologist. She holds a BS in biology from Yale, and a couple of our board members are also Yaleys. Right? She's a PhD in oceanography from Scripps, and she has worked with other policy organizations, with the American Association for Advancement for Science. And she's been a Congressional Science Fellow in the U.S. Senate and a fisheries researcher at CERC here. And she still continues her scientific program on shoreline restoration and ecology issues. That's fabulous. So I'd like to invite Dr. Davis to the podium to take over as a moderator, all right, for our discussion, and to invite the audience here to participate, all right, in the discussion that you just heard. Thank you, John.
Thanks, and I'm really honored to be here and to help organize the discussion with our two speakers. I want to thank our speakers. They were really interesting presentations. Yeah, maybe we want to have both of you come up. And I encourage the audience to think of any question completely outside or inside the speaker's expertise, because they love answering questions that, you know how scientists are. Yeah.
That terrible graph with our estuary going to Florida does not reflect the water level at all.
No, it's the temperature.
Right.
Yeah, it's a way to.
They're going blue, blue, blue. So,
No, it's just a way to. I think it very effectively expresses the projected temperature change.
What I thought we might want to do is start by just sort of summarizing some of the key points that we heard, and throw some out there if you think I'm missing some, because I think it might help us organize our thoughts. So I'm going to just run through quickly what I think we heard from both of our speakers. So Tom spoke a lot about the idea of variability, and the first point that I learned is, do we have any engineers in the crowd? Yeah, so what I learned is that biologists are much smarter than engineers. So that's the first point that I think we should keep in mind. Is that a fair assumption?
It's not rocket science, it's a lot harder.
Right, so we learned about variability, and we learned about the fact that it's going to be tough for us to deal with a number of different pieces of the variability in the fishery story. We also don't know the impact of change on that fishery story, and we don't have clear goals. So that's sort of one piece that we learned. We learned that there was one pretty simple equation that guides fisheries, and that really the four sort of factors there are growth, recruitment, fishing mortality, and natural mortality. And right now we focus on the management on that fishing mortality. And he promised us we wouldn't see any more complicated equations, but of course we did. We saw a lot more complicated equations. But that's one piece. I think I'd like us to think about, when we think about what we can do, that we have these 4 parameters and we're focusing on one, but can we do something about the other ones? And Tom touched on that a little bit. And we learned a lot about the possibility that we actually could change our process of fisheries management from invite, inform, and ignore, which I quite like to describe our council process, to something that really engages stakeholders a lot more. So I know this audience is a very active crowd and a very sort of action-driven crowd. So when we think about these talks, let's think about things that we can do. And I'm thinking about this for ourselves, myself too, and also my organization. So from Dr. Najjar, we heard, is Senator Inhofe in the crowd by any chance? Yeah, right. So, no, I'm not going to make this political, but just in case he showed up, we did hear that warming is human-induced and pretty likely driven by fossil fuels. Is that fair to say? Oh, yeah. Right.
And I'm happy to. I know there appears to be a debate about that, but among scientists, particularly climate scientists, there's really not a debate about it.
Yep.
It's not like we've got everything figured out, but the basics. That CO2 is going up, it's too humid, it's greenhouse gas, causes warming,
right.
Causes sea levels to rise.
A fun topic of discussion for us tonight might be this fair and balanced media piece and how we find the one scientist out of 1,000 that maybe doesn't agree with that point. We heard that sea level has already risen, so whether you believe in climate change or not, sea level is already rising. And we heard that there are certain things we're very certain are going to happen, certain things that we're pretty certain are going to happen, and certain things that are likely to happen. And all of those combined are going to affect our fisheries. In some cases, it's not necessarily all bad. We might have increased growing season. But in general, it seems like most of the impacts are going to be negative. That's a fair assumption. We also learned that there's things that we can do. I'd love to see a conversation about the sort of eat more veggies, eat less meat piece. And let's think about the nitrogen piece of all that. Certain fishery scientists, like say Ray Hilborn, are pretty adamant that we should be eating a lot of fish relative to meat. So that's fun to think about, kind of the nitrogen and the phosphorus and kind of where it all fits together. We heard that New Yorkers will probably come here instead of going to Florida in 100 years. That's pretty scary. Sounds a little bit like a Seinfeld skit. So we heard a lot today, and I think that there's a lot of really fun themes that kind of run through the talks. And again, I'm hoping that we can focus a lot of the discussion on what we can do as organizations that we each represent and also as individual citizens. So with that, I'd love to open it up to the crowd. A lot of folks. How about we'll start over here?
Dr. Miller, you presented an interesting approach to bringing in stakeholders, and I know that you also worked on COP. Being a New Englander from Boston, having grown up on COP, has that approach been used in the cod fishing?
No. So I have to say, first of all, I worked on cod, I worked on a fish called bloater in Lake Michigan, I worked on crab. All of those fisheries went down the toilet while I was working on this. It has nothing to do with why I'm working on them. No, when there is a strong commercial interest and there's not multiple stakeholders, there's really no pressure to have another interest voice in there. And it's the question of how well can managers represent society? And I would argue that managers have failed to represent society.
We have a question in the back.
Yeah, I guess rather than, there's a question before what we do, and that question is why we care. And I unfortunately spend most of my life in D.C. where we do a lot of stakeholder meetings. And what I find with stakeholder meetings is you try to solve every problem simultaneously and you come up with a pretty rotten solution. And sometimes it's better, it's a more productive approach to set priorities, but to understand priorities, you need to understand what are you trying to accomplish. As I think Dale Bumpers once said, when they tell you it's not about the money, it's about the money. And one of my other lines of it's really valuable to the people who live around it. It is one of the most unique bodies of water in the world. This is one of the most unique estuaries of the world. It brings tremendous economic benefit to the entire region. So then it maybe gets us to your time, we're talking about who makes the sacrifice. Sacrifice is a whole lot easier if we all understand what we're sacrificing for. So I just wondered, my question to you all this would be, have you articulated why we should care about this?
So I would say that when we went into this example in Florida where the commercial and recreational and the NGOs all got together, I was expecting the answer that you just gave. Because we asked them first, what are we trying to do? Because until you tell us what we're trying to achieve, we have no hope of having a reasonable discussion. And I was expecting that. The value of the fisheries, the value of the recreation, the tourism, all of that, that wasn't what it was. Everyone, the commercial fishery, the recreational fishery, the NGOs, said we need to leave a world better for our children than we have inherited. And that was what they agreed on, and that's what they wanted. They were willing to forego their own personal economic benefit in the short term if they were convinced that it would leave better conditions for their children.
Then if you start with that priority, you start with that objective, then you need to lead to the priorities list rather than a stakeholders approach, which is what I'm sort of suggesting.
Dr. Miller, a follow-up question on that. Do you think did that take a while to develop that goal? It seems, I think some of us might be surprised to hear from an industry, rightly so, that would be the goal. Did it take a while to kind of settle on that goal?
No, I was genuinely surprised because I would have thought the same thing that was behind your question, that a commercial fishery operation would have really worried about this year's profit or profit for the next 5 years, really wouldn't have worried about the future. But what marks a commercial fisherman is different from me is, first of all, they can go to sea without being sick. But the other thing that marks them as different is that I really don't care if my children don't grow up to be academics. And my parents certainly weren't academics. For commercial fishermen, for most commercial fishermen, it's what their forefathers were, and it's what they hope their children can and will be. And that marks it as a very different kind of career, if you like, than the careers most of us have.
I'm just trying to translate that into what we see here in the Bay with some of the other issues. And it might be that there is a fundamental difference there that might lead stakeholders in different sectors to kind of have a harder time coming up with that as the goal. But it's an interesting point. Yeah.
Did that answer also come from the Omega protein company?
They were involved in that, and perhaps when you get corporate fishing, perhaps you don't. But in Florida, as in the Chesapeake, the majority of the people involved in the fisheries have that goal, not perhaps the corporations involved.
I was struck recently by an article in the Capitol which had a picture of bluefish and an oyster. Blue crab and oyster, saying that increases in C2O increase the size of crab, and I thought, oh, good, more whitening. But that it was very bad for oysters. And what I thought about it is that if this is going to work, one has to translate this into things that non-technical, non-professional people can understand. And I thought that was a really good article for bringing home the effects of what's happening to the average person. And I think one of the things that happens is that a lot of this does not get translated into language that non-academics really can understand, or politicians, because politicians are going to look for what's going to get them votes, and it's not really academics that are doing that. And I picked up on that as something that I think that the technical people really need to think about. How do I explain this to the average Joe?
We'll go here first and then Tom.
So if I can return to the Florida, you have different interests there. Better is, in the eyes of the
The other was to agree that everyone in the room was a legitimate stakeholder. That they weren't in the room for political reasons, for whatever, subversive reasons. They were there because they were a legitimate stakeholder who had a valid viewpoint in the question. And if you don't have that acceptance that the person sitting along the table from you has a valid view to be expressed, then people will ignore it. And in the end, the commercial fishermen were arguing for policies that would benefit the recreational side more. The NGOs were arguing for policies that would lead to dinner-sized king mackerel to go on the plates. I was a skeptic going into it. I thought the best we would get out of it was a group hunt. And what we got out of it was very, very specific management advice. It was section specific.
Is this a framework that could be useful as the Magnuson-Stevens Fisheries Act is being reconsidered, reauthorized?
I would love to see the people like me who do stock assessments forced to explain it to people who we are, whose livelihoods and whose beliefs are impacted by the decisions that we make.
Yeah. Tuck, you had a question?
Well, that's all very good about improved management for Chesapeake Bay now, but what I'd like to think about is what Ray said with, what things will be like 40 or 50 years from now, which is where our kids will be our age, right? And so what's really driving this is the fact that the world population is going to go from 7 billion to 9 billion. The U.S. population is going to be approaching 400 million. And the Chesapeake Bay population, watershed population, will be up about 20 million, right? And we've got to feed all those people, and that climate change is going to do what happened last summer. So eating less meat isn't going to be only the problem. There isn't going to be more meat to feed those people produced from the heartland of the country because there's not enough fresh water to grow all that corn and beef and all those things. What's going to happen is put more pressure on seafood, and probably the thing that can be changed in that simple equation is the R, the recruitment, which is going to be supplied probably like it's being supplied in the rest of the world now by aquaculture. It's going to change the whole habitat sequence of what's happening in Chesapeake Bay, for example, or other systems. So suddenly our ability to manage everything is going to be very different in concept from what we have now, although I would argue that your issue of stakeholders and fitting all of those things together can still be a valid political approach, but it's going to have to be rethought rather than in the traditional way that we're viewing fishing by changing out.
So,
how's that?
They're speechless.
Let me say a couple of things in response to that. I think aquaculture will grow more. I think there are problems, however, with the current form of aquaculture that will limit the growth, but I think we will solve those. One being that still we need fish to feed fish, but I think we'll solve that question in the near term. But there are lots of people who have a legitimate stakeholders in managing the Chesapeake Bay fisheries that aren't just commercial fishing, that will still want to go out and catch striped bass, that will still want to go out and be able to pull crabs off of their dock or off of the bridge to feed, that aren't high capacity fisheries in that sense. So I don't think it will completely change the way suggested.
I have a question about that equation as well that takes us slightly on a different tack into the restoration world. So, Tom, you touched briefly on the fact that we might actually be able to change R through habitat enhancement, for example, and M, the mortality, through also habitat enhancement if we can provide additional refuge. So those of us who work on habitat restoration types of practices think about that all the time. we use it as a justification to support our work, but we have absolutely no evidence that we can actually do that, really, I mean, to be honest. And then thinking about the fact that folks are always saying to restoration folks, and I think everyone here has probably played a role in planting a restoration project. Joe and Will do them every day, and some people, hang oysters off their docks. So we're all kind of engaged in this restoration front, but we don't really think about the impact of climate change on how we're planning restoration projects. So I know those are sort of two questions, but Barry, do you want to address this first? What should we be doing as folks who deal with restoration thinking about climate change?
Well, I mean, I guess you need to engage the experts in those particular habitats and have them, if you're restoring a tidal marsh or an oyster reef or SAB beds, and you're really thinking out 20 years, and we might see a degree Celsius change. That looks like that's going to be significant for that particular habitat, and maybe it's not the best thing to do, or maybe you want to do it somewhat differently. I think there's also a lot of research questions in there about adaptation and evolution of organisms as the climate warms. So, it's not clear exactly what one does exactly, but we can't pretend that it's not going to happen. And just, think about the past being a model for the future in terms of physical environment.
Tom, did you want to address that as well?
No, I think Ray perfectly, given the length of time that we suggest our restoration projects are going to be effective for, that really is coming into the timeline where climate change is going to be a real impact.
Yeah.
I don't think with regard to what's happening in the Bay now, I'm not sure I would say, scratch the TMDL because climate change is going to change everything. I would not say that. But it's just something we need to keep in mind as we, it's this whole adaptive management framework. We're going to learn as we go. There's a lot we don't know. I mean, everything I showed, a lot of it was pretty qualitative. And, how important all those arrows really are from my boxes to dissolved oxygen, so a lot of it still needs to be sorted out. These are some of the things we should have in mind, and to drive certain research questions. We need to keep monitoring the data. It's really monitoring our estuary, because the systems are so complex that we can throw all our models at it, all our laboratory experiments at it, but the real example or the real data that's going to show us how the system really works is when we observe it and experience some change.
We had a question by the gentleman on the edge. Do you still have a question?
Oh, I was just wondering what the chances are. They say if global warming continues, you have a lot more ice melt, say Greenland, up in the Arctic. And they say that could, that water going down, the denser water, could actually change the course of the Gulf Stream. Right. You guys are, you're planning, what do you say? Is that something near future? Or?
Well, some argue that that's actually already happening, and what the slowdown of the Gulf Stream does. This is what's going on here is that fresh water is getting into the North Atlantic, and water can't sink there as fast, and that means it can't be fed as rapidly as it was in the past with Gulf Stream water. So the Gulf Stream slows down, and that actually has an effect of the sea surface slopes up towards the Gulf Stream. When it slows down, it kind of flattens out, and that lifts up the sea level along the coast. And we have observed that. The Mid-Atlantic region is this hot spot for sea level rise. And this is even after you take out the subsidence effect. So it could be something that's already happening. The way I have thought about with regard to Mid-Atlantic estuaries is to, there are some calculations that project into the future how the Gulf Stream for change. And there is a lot of consensus. Models do, this wasn't the case 10 years ago. The climate models now show a lot of consensus for weakening the Gulf Stream and for enhanced sea level rise along the East Coast. I mean, it's not, it's on the order of another 10 or 20% more sea level along the East Coast than you would get, say, in the middle of the Atlantic Ocean or the Western Atlantic. So that's how I've used that information.
If anyone's a waterfront property owner here, that 10% might actually be pretty important.
Yeah.
Yeah.
That would also affect the winter temperatures as well, right? Ambient temperature.
The slowdown in the Gulf Stream actually makes, it's a natural warmer for the North Atlantic. And so when you look at projections of global temperature change, you see warming over the land, and it's not as much warming over the ocean. But the North Atlantic actually shows up as this place where the amount of warming is the least, because the Gulf Stream is slowing down. So it's not actually cooling like the Day After Tomorrow movie. It's the same idea.
I was going to say, isn't Will Smith involved in this somehow?
But it is a weakening of the warming.
Yeah, I had a question for the whole panel. Recently, I read a number of articles on top-down ecosystem as opposed to bottom-up ecosystem, which is what all of this our general thoughts are about. And I just wondered what your opinions, impression was of this, the bigger guys eating the littler guys, etc., and how that fit into the boxes and squares that were there.
So you're quite right. The classical view of ecosystems is that they are regulated by the amount of energy flowing up from the plants, the phytoplankton, all the way through. There's fairly compelling evidence of a process that's called top-down control, where if you change the number of top predators, it affects their prey, and if there are fewer of their prey, the prey of my prey increase, sort of thing. And there are clear examples where that happens. There are clear fishery examples where that happens. There are clear management examples where that has occurred. But ultimately, it's still got to be controlled at some point by the amount of energy going in. At some point, because if you have less energy being fixed, or if you have more energy being fixed, the whole system will move up and down, just the relative balance.
Yeah, except their argument is that it's either energy coming in or it's the energy that's
and the answer is it's both. Right?
Yes, obviously. So how would you tweak your models to think about
So they've done that experiment in Wisconsin, for example, where this idea first was given birth. A fellow called Jim Kitchell, a colleague of mine, convinced the state of Wisconsin to put their entire walleye production for 1 year in Lake Mendota. And the argument was exactly that. Lake Mendota, which is where Madison is, was green. And they had tried and tried and tried with nutrient reduction and sewage treatment, and Lake Mendota was still green. And Jim came in and said, we put all the walleye in there, and they'll eat the planktivores, which will allow the zooplankton to get big, which means they will eat all the green stuff. Right? Every walleye in the state of Wisconsin produced went in there. It was a very cold winter that year, they all died.
I love walleye.
But it's been done on a small scale, and you can change the characteristic and the amount of phytoplankton.
So the
by
phytoplankton response
by stocking.
Yeah, which is, I think, is an interesting concept that has not really been fed into the bottom-up equations that it would be in. Kind of fun.
But that's what fishing is, right?
Yeah.
Fishing is top-down
Yes,
control.
exactly. Yeah.
And so if you ask, does top-down control occur and can it be effective? Talk to people from New England who remember what it was like when cod were there. The ecosystem's different because of top-down control.
What about when some have argued that oysters, filter the bay with much higher rates and then that's one reason why the bay was so clear, the phytoplankton levels were so low. I mean, something I've heard, but I really don't know what.
So most of the models will suggest exactly that. And when these ecosystem models were first brought forward, they were brought forward in the company of DNR managers and federal managers. And the first challenge they were given was, let's pretend we met what was then the 2000 goal for oysters, which I think was a 10-fold increase over their baseline. Let's pretend we were successful. Tell us what would happen to the ecosystem. And so the modelers went away that night, and they came back the next morning and gave a presentation. And they said, if we achieve the oyster goal, striped bass decline precipitously. And the manager said, one of the managers said, that can't be. And the modeler said, well, I was very careful how I put the numbers in. I really checked this, but I'll go back and check it again. And the manager said, no, that can't be. And then they realized what the manager meant was, we can't have goals where we can't meet both of them at the same time. And it never crossed their mind. The goals that they were setting independently were in fact in conflict with one another because there are these trade-offs that occur. So we could have perhaps restored oysters and find that it locks up all of the energy in the benthic ecosystem. And striped bass are not as productive as they are.
Which gets back to the baseline question. What do you shoot for?
Yeah.
What is your goal?
What's the goal that society wants?
Yeah. Yeah.
I wanted to follow up on a comment that you made, Jenna, with respect to restoration, and a question for Tom about in the discussions that you had with the stakeholders in Florida, and you sort of put to them that there's a fixed amount of pie to divide out. I think that's a very effective way to present it. Was there any discussion and interest in
everyone can have what they want anyway, right? Which is I don't think we can ever make the pie that big. But that certainly in this region would be, I think, a very valid question for the stakeholders to consider. If we made the pie bigger, would the trade-off be such that you could live with the outcome?
We had a couple of hands up earlier. Yeah.
I want to come back to the issue you raised as far as mutation and evolution with regard to changing habitat and environment. We certainly had the example of the Darwin finches, and there was recently a report, I think it was with the Sonopos, but I'm not sure, they found that over about 30 generations they were finally able to reproduce in the lab a selection directed. Is that something that is even conceivable for the aquatic environment, or?
Yeah, I was just at a workshop on sustainable habitats in eastern Maryland, eastern shore there, and what's it? Eva Marie Koch, I think, told or someone had mentioned something about the SAV, submerged vegetation, eelgrass, I believe. I hope I'm getting this right. But that there was a heat shock, and that kicked back, knocked out a lot of the SAV. But then successive heat waves, I think in maybe the next year or later years, that were as potent, did not seem to have as bad an effect. So it's almost like, I think it's a speculation that the initial extreme heat wave had basically, selected for the most heat tolerant. I don't know. This is really the edge of my knowledge here. Genotypes. And so that they were able to fare better the next time heat came around.
But I think there is one important restriction. One of the questions you raised was about ocean acidification. And the issue with acidification is that many of these organisms are calcifiers, and they deposit calcium carbonate in their shells. Crabs put calcium magnesium bicarbonate in their shells. There's a physical dynamic that controls that. And enzyme systems might get better at scavenging carbon
question related to that. We're putting a whole lot of effort currently in oyster restoration in the bay. Eastern Wisconsin. One wonders about that when one looks at acidification on both Pacific Northwest and in the southern part of Chesapeake Bay. People that are involved in producing larvae are having a hell of a time. People that are involved in producing oysters are having a hell of a time. And I think it's only going to get worse rather than better. So the question back to restoration, are we putting the right amount of buck for the right amount of thing now, knowing what we know about what might be happening to the critters we're trying to, we're putting so much effort into trying to preserve or restore. Any thoughts about that?
Well, it doesn't really answer your question, but one other aspect of the acidification problem is related to the hypoxia problem. When you have too much respiration in the deeper part of the water column, that actually increases the acidity as well. So solving the oxygen problem can in part help us solve the acidity problem too. In other words, we've actually, there's an acidification that's going on that's independent of atmospheric CO2. So and I think the trends in pH in the bay are not, it's not all going up as you might expect from CO2 because you have these other factors affecting pH.
Yeah.
Don't the Menhaden, alkaline bunkers, they eat a lot of the algae, and my understanding is they do an excellent job and often clean up the bay. I always wondered about the standard they set for the amount, the volume of those things that are being caught, whether that's way too high.
So you're right, they are filter feeders. They do as adults, they remove phytoplankton from the bay. But they also eat a lot. And that releases nutrients. So they don't, when oysters do it, they bottle it up, put it in sort of pseudo-feces, in particles that are down on the bottom. When fish in the water column filter, they regenerate the nutrients that they've just consumed. So they're not quite as effective at changing the whole ecosystem in the way that oysters do.
I think we have time for one more question.
Well, if it is possible to reach consensus on what the objective is, which you did in Florida, and if we could get consensus on preserving the bay in current conditions is valuable, then it would seem to me that it would be very helpful to have the scientists like yourself to give us the 10 most effective steps we could take to accomplish that, or 5 or whatever, but
or 2.
Because some things we just don't have control of. I suspect we're not going to halt global warming in the Chesapeake Bay District. I suspect we're not going to do that. But you might be able to suggest something else we can do that would have immediate impact here. But I think my question to you is, isn't this where the scientists come in? Because if the public agrees on the objective, you'll have political support. And then the question is, what concrete steps do you take to achieve the objective?
So my first one was the one that I gave you, which would be to set an absolute cap on the total biomass that you can harvest from I don't think there's any... Sorry?
I'm sorry, I can't hear you.
Oh, my first step, I've not thought more clearly about the top 10, but the top 1 would be to set, you want 3?
Yeah, come on, time 3.
We'll start with the top 1. The top 1 would be to set a total cap on the amount of biomass that you can take out of the Chesapeake. I think we can estimate that defensively, and I think the benefit of that is that it forces people then to consider the trade-offs. It puts them in a mind where they have to confront the trade-offs. Give your top 1, and I'll think about what I'll say.
I I realize climate change is a global problem, but I still think that, something we need to act on. And I've sort of crossed over from being neutral about this. And, I'm just a scientist. I provide information. You guys decide what you want to do. I've reached the point where, we do all this research and they'll make all these predictions, and then it would be a tragedy if they all just came true. So I'm happy being an advocate now. I just think it's the right thing to do.
Wouldn't nitrogen production be up to
Say it again?
Nitrogen reduction, wouldn't that be up to nitrogen? You mentioned that earlier as a
Yeah, okay, so with regard to vulnerability to climate change, a more resilient bay is going to be able to deal with, climate change. And so it's a no regrets strategy, I feel like, to keep pushing on doing the things we're doing to restoring the bay, TMDL, try to improve the water clarity, increase the oxygen levels. All of that is going to make the bay more resilient to climate change. So it's basically keep doing what we're doing. I wouldn't change that, the general thrust of the cleanup effort.
So Ray gave us 2, support climate legislation and keep going with the TMDL. So Tom, you have to come up with one more.
My second one, I would fundamentally reform the way fisheries management is done. I would take managers out of the middle and make them subservient to the stakeholders.
Who are the stakeholders?
That comes in part from this decision of what the goals are, but they would have to include clearly the commercial fishing interest, they would have to include the recreational fishing interest, they would have to include the environmental interests. I think there has to be a consumer interest, because the consumer interest has never been represented in fisheries management at all. And there has to, the state has a role. It has this natural trust doctrine that it has to adjudicate between. But to set the managers up as the sole person performing what's good for the society, I think is too big a burden on managers.
Well, I think that's a great place to conclude. It gives us 4 specific actions that we can either take ourselves or support. And I'm sure that the West Riverkeeper folks who have a display in the back can help us with really more specific individual actions as well. So plug for our Riverkeeper partners. And I want to thank you for having me here. And I'm going to turn it back over to Al.
All right, thank you very much, David.
I'd really like to thank our presenters. I didn't expect that we would have answers to the questions. I was certain that we would generate more questions than we would answer. And unfortunately, that is the case. I wish it were more like physics, where we could do a quick computation and come up with the answer and solve the problem. I would really like to thank our presenters and Jana for taking over and being our moderators this evening. With that, I'd like to bring things to a close and thank you all for coming.